Oh, well, thank you all for coming. I appreciate you being here. My name is Leemon Baird, and I'm going to talk to you briefly about Hashgraph. This is a consensus algorithm we have, a distributed ledger system. Swirlds is our company that's doing it with permissioned ledgers. At the moment, we don't have a public ledger. We don't have a cryptocurrency. So if you ask me, tell me about your cryptocurrency, I don't have one. I always get that question. Right now what we're doing is the permissioned ledger, but they would both use the same consensus algorithm. And so I'm going to talk about that today. And I have been told that we're going to have a mixture of people who've never heard of blockchain and then people that are deeply into this and are experts of it. And so that's great. I'm going to start at the very beginning, and then I'm only going to talk for a half hour, and then we can have a half hour of questions. And so if you want to get into the very deep details of the math, I'm happy to go into that. But if you want to just talk about various business applications, I'm happy with that. And if you want to just say again, now what is this blockchain thing? That's great too. So we'll just go through this for a half hour. So what is Hashgraph? Hashgraph is a distributed ledger technology. It's a consensus algorithm that you can use for a DLT. DLTs are systems where a group of computers are going to be sharing some information, and we don't trust each other. You don't particularly trust any given computer in the group to not corrupt the data, or to not change the data, or lie about it, or try to stop us from coming to consensus. But we do trust the group as a whole to not have too many bad players in the group. If you can't trust anybody, then you're out of luck. But if you have a system where we have a group of people, a group of computers, and we can trust that we won't have a large group of them ganging up on us to corrupt the system, but we don't trust any single one person, then what a DLT does is it allows us to come to an agreement, a consensus, on the order of our transactions. So we're going to all be creating these transactions that change our shared data in some way, that do something. And we're going to come to a consensus on what the order of that transaction is, of what all the transactions are, what order they are. We're also going to come to a consensus on a timestamp for each transaction. So for every transaction, we're all going to agree, here's the time at which it officially occurred. And in Hashgraph, it's actually going to be a good timestamp that we all contributed to. In some systems, one person can arbitrarily make up the timestamp, but everybody else has to sort of approve it in some way. But for Hashgraph, it'll be a good timestamp. So this is what a DLT is in general. Lots of people talk about blockchain. Sometimes when someone says blockchain, they mean DLTs in general. So in that sense, we're a blockchain. Other times when someone says blockchain, they're talking about a certain kind of DLT. DLTs that are built out of a chain of blocks on top of each other, connected to each other. We don't have a chain of blocks. So in that sense, we're not a blockchain. But we're a DLT. So we are doing the same thing that the other DLTs are doing. And if you're one of the people that uses blockchain to mean all those, the whole DLT world, then yes, we're a blockchain as well. But I like to make the distinction, we're not built on a chain of blocks, we're built on something else. So this is what Hashgraph is. It's the consensus algorithm. It's the way that the computers are going to talk to each other and come to an agreement on the transactions and on the other things. And Hashgraph is fast, it's secure, and it's fair. These are the three main things that we want in a ledger. And what you'll find is that it's faster and more secure than these other ledgers, and it's fair in a way that the other ledgers are not. So there's some unusual things about it. And the reason it's unusual is because it achieves this consensus in a totally different way. It's just very weird. Not at all like what you would see in all of these existing systems with Bitcoin and Ethereum and Paxos and Raft and PBFT and Casper and IOTA. You may have heard of all these different systems. They all work in different ways. Hashgraph works in a very different way. In fact, Hashgraph goes back to these 30-year-old voting algorithms that we've had for decades and extends it. So we'll talk about that. So let me just say what these things are. What do we mean by fast, secure, and fair? Fast in what sense? Well, secure in what sense? Fair in what sense? So here's what we mean. For any ledger, these are the things you might ask, is how fast is it? For fast, you want to know how many transactions can we do every second? So if it's, say, a cryptocurrency, I want to know how many times per second can I do a payment? If you had a credit card system, it might be 10,000 payments per second, 10,000 transactions per second. If it's Bitcoin, you're more like 3 transactions per second. Different systems have different speeds. And then the other thing is latency. When I do my payment, how long is it before I know that the payment went through? And I know that everybody else knows that it went through. And I'm guaranteed mathematically that it went through. So two things, throughput and latency. For Hashgraph, the throughput is hundreds of thousands of transactions a second. We've done experiments that go across the country. We've done experiments that go around the world. And you can see very high speeds. And we also have very low latencies. A few seconds or even a fraction of a second from when you create a transaction, you try to pay someone some money, until you have a cryptographic proof that the entire community has agreed on the ordering of your transaction and that it really will go through. And it's a cryptographic proof that you could actually take to a court to prove it. This is also something that's a little bit different from some ledgers. It isn't one of these things where every time I get a confirmation, I become a little bit more sure. No, you reach a point in time when you know for sure. So if somebody pays you at your store, you can hand them the product. You can say, yep, I am sure it went through. I know I'm going to get to keep the money. And so then you hand them the product. So this can be fast. There's lots of caveats on speed, by the way. If your transactions take a long time to process, it takes you a year for your supercomputer to process a transaction, then your network's only going to do one transaction per year. This is just the consensus part of it is incredibly fast. You basically turn it into a network for free. So that's what I mean when I say that this Hashgraph thing is fast. It allows us to do these ledgers that are fast, which opens up new kinds of things you could do, like games that you couldn't do before. In addition to that, it is secure in the same ways that the other ones are secure, but also in some new ways that aren't really being talked about a lot. So it is secure. The math term is asynchronous Byzantine. It's Byzantine fault tolerant in an asynchronous sense. This is the strongest form of security. I told you that this goes back 35 years. For 35 years, the gold standard in security has been asynchronous Byzantine. Then some systems aren't quite as good as that. They're partially asynchronous, or they're synchronous Byzantine. And some are even worse than that. They aren't Byzantine at all. They aren't anything. They're just, well, we're pretty sure they're safe. But if you have math proofs that are really strong, you can say it's asynchronous Byzantine. What does that mean? It means that we as a community, when you have two transactions, we as a community are going to come to an agreement on what order they're in, and we will know that we've come to agreement. It isn't just that you think they're in this order, then you think it's this, and you think that it's this, and that eventually it stops swapping. It isn't just that. It's that you know when you've reached agreement. So if somebody pays you some money in your store and you're afraid that maybe your coin's going to disappear because they also paid somebody else that same coin, you're afraid it was a double spend, you have to wait until you're really sure that your spend came earlier in history. In some systems, you just become more and more sure over time, but you never really know. In Hashgraph, there's a moment, in any Byzantine system, there has to be a moment when you know for sure that you have the right consensus. And you have to have a mathematical proof that you will never be wrong, given the assumptions that not too many of us are bad. By the way, the assumption is usually that no 1/3 of us are evil and colluding to corrupt the system. There's actually a math theorem that says you can't do any better than that. No system could be resilient to more than that. But the best you could do is getting up to 1/3. And Hashgraph does that. It gets up to 1/3. So this is the best you could do in a Byzantine system, an asynchronous Byzantine system. Also, I said we don't make I said you have to make assumptions, like we won't have 1/3 of us being bad. We also assume that the internet can do bad things, or that bad people can do things to us over the internet. For example, what if the bad guys are able to set up a firewall around a big chunk of all of our computers and shut it down, basically partition the internet into two halves? Or what if they can do something even worse and have some of their computers talking through that firewall, but other computers can't? Or it slows down your messages by arbitrary amounts, or it deletes some messages and not others. We're resilient to that. If you're asynchronous Byzantine, you're resilient to that. If somebody says they're Byzantine but they can't say asynchronous, what that means is maybe their system isn't going to be able to survive a malicious firewall. And do we have firewalls in this world? Sure, all over the place. Some whole countries have firewalls around them. So we want to have a system that's secure in a world that has firewalls because we happen to live in a world that has firewalls. And there's an even bigger problem. What about botnets? What happens if bad guys out there are able to hack into little computers on the internet, computers you don't even think of as being computers? Like, what if they could hack into your printer and take over your printer? Well, you'd say, I don't care. So they can print something. So what? Now, here's the problem. If you take over enough printers, you can have them all send messages to one person over the internet and flood them with so many that their computer can no longer receive or send messages from anybody else. You can shut them down with a distributed denial of service attack. That's a big deal, and that has happened. This is a big deal in the media. The Dyna attack last fall shut down people like Netflix for hours. Does Netflix mind if their servers go down for several hours? I'm guessing they probably do mind. Yeah, that's probably not a good thing. When you're entirely dependent on the internet for your business, you probably don't want to be shut down by a DDoS attack. So for these ledgers that we're building, we want to make sure they're not going to be shut down by a DDoS attack. So what you want to do is prove that it's Byzantine, which means it'll keep running, and you'll keep getting consensus, and everything will be good. But you want to assume that we live in a world where sometimes DDoS attacks happen and where sometimes there are botnets. And again, that's what the asynchronous means. If someone proves Byzantine on some system but it isn't asynchronous, then that means maybe it could be shut down by a DDoS attack. For example, leader-based systems. Paxos and Raft and PBFT and some of these leader-based systems, even some of the distributed proof-of-stake systems where we take turns being leaders. The problem is, even if you're taking turns being leader for 2 seconds, if the attacker can shut down one computer at a time, then they can shut down your entire network because they'll just shut down your leader. And when we move to a new computer being the leader, they'll move to attacking the new leader. And they'll just keep following the leader and shut us down as long as they want by just shutting down one computer at a time. So that was a lot to cover, and actually had a lot of math words in it. And yeah, it's inherently mathematical. But the important thing is you want to be secure. All of these ledgers care about security. If you didn't care about security, you would just use a single server. Why even bother with a ledger? And different ledgers have different kinds of proofs of their security, and the strongest you could do is asynchronous Byzantine, and you want both of those words, both the asynchronous and the Byzantine. And so the Hashgraph has that. And most of the algorithms aren't asynchronous Byzantine. That's a very rare thing. Except, of course, for all those algorithms from three decades ago. They're asynchronous Byzantine, but they're so incredibly slow you'd never use them. However, Hashgraph is not slow, but it's still asynchronous Byzantine, and it also has a new property that ledgers usually don't talk about at all, and that is fairness. In fact, we have 3 different kinds of fairness here. So we want to have our ledger putting the transactions in order, and we want to have good timestamps on them. Honestly, if you're doing a cryptocurrency, you don't really care about this very much. Maybe fairness of access. You don't care about the other kinds of fairness. But imagine if we use these ledgers for other applications, like a stock market. So imagine this. We're going to have a stock market, but we're not going to have the New York Stock Exchange set up a computer that we all have to trust New York Stock Exchange Incorporated to be honest in their computer. Instead, we're going to let each of the brokers have a computer, and those computers themselves are the stock market. There is no one else. There is no stock market corporation involved. It's just the brokers themselves being the stock market. And they don't trust each other, definitely. But there's enough of them, let's imagine, that they can assume that no 1/3 of them are going to gang up on the rest. In a stock market like that, every time you put in a bid or an ask, every time you said, I want to buy a share of IBM at this price, or I want to sell a share of IBM at this price, your bids and asks are going out, other people's bids and asks are going out. You want the stock market to match them up. And you could say something like, well, when I offer to buy something, the first person who offers to sell at that price matches up with me. Or when I offer to sell something, the first person who offers to buy at that price will match up with me. If we do a stock market like that, then we start to care a lot about exactly what order the transactions are in. If you put in a bid, and I put in a bid, and mine, actually I put it in later than yours, but I could bribe somebody and get mine to count as before yours, that would be bad. People spend millions and millions of dollars just to shave milliseconds off of how long their bids go into the stock market. This is an incredibly important thing to stockbrokers. They would never use a market where it was possible for one individual to arbitrarily reorder some of the ordering, or influence the bids and asks into a bad ordering, the way they want it to be. In Hashgraph, what we do is we have fair ordering. When you send out your transaction, it's going to go to the community as fast as possible, and you're going to get credit for it when it reaches most of the community. And when I send out my transaction, I'm going to get credit for it when it reaches most of the community. And whoever reached most of the community first is going to count as being first. And there's no one person that I could slip some money to that would get mine put before yours. If you reach the world before I reach the world, then you get credit for it, guaranteed. So we have fairness of ordering. We also have fairness of access. If you want to go put your bid into the system, it's really hard for anybody to stop you. You can put your bid into the system very rapidly. And it's resilient in ways that it's hard for anyone to stop you from doing so. And you can get it in very fast as well. Furthermore, in a fraction of a second, you can get it in the network, even if some of the nodes are bad and they're just being mean and not accepting your transaction, you can still get it in. So we have fairness of access, we have fairness of ordering, and we have fairness of timestamps. When we get a timestamp put on your transaction, it will be something that the entire community helped contribute to. So for example, in legal contracts, there might be a legal contract that says you have to send out some information before noon on Tuesday. Well, when you send out the information, it gets a timestamp, and then you can trust that it is the community as a whole has helped contribute to that timestamp. And so you can go to a court and say, yes, I really did do it by noon on Tuesday. And it wasn't just the opinion of one miner, it was the whole community contributing to this timestamp. So these are the things that we would want. We want something fast, secure, and fair. We can do all three of those in Hashgraph. And what it does is allows us to start doing new kinds of things we haven't done in the past, new applications. So let's forget about Hashgraph for a second. Let's talk about ledgers in general. So distributed ledgers have been around for a while. You could say they go back 30 years, although really that's more of the distributed computing and the fault-tolerant community. You might say, well, really it started with Bitcoin, was the first blockchain or the first distributed ledger that we're going to call a DLT. So let's just start, say, with Bitcoin as our history here, and talk about the generations that we've had. So what happened? You could say Bitcoin came along and said, you know what? We could do money without any government. We could do something better than the fiat government, the fiat monies that are out there. Revolutionary concept. We'll do it by making people do proof of work. So you buy a supercomputer and you feed lots of electricity to it, and then you too can help be part of the system and make it fair. And it's so hard to do that that we can trust that no one person can dominate it, and so therefore we're all going to be fair and trustworthy, and we will ensure that the ordering of our transactions are agreed on by all of us. It may not be terribly fast or fair, but we'll agree on them, and then nobody can forge money. No single government, no single person would be able to forge money in our system, counterfeit money. Kind of revolutionary. And there's a lot of applications for that. And even at 3 transactions per second, you can see that there's an enormous market with Bitcoin. I mean, it really is a big deal. And that is the first of the 4 generations I'm going to talk about, but nothing stands still. It's continued to improve. And even today, people are continuing to improve this. So what does it let us do? It lets us do things like these examples here. It lets us use cryptocurrencies like you would use money. You can just save some of your money in your cryptocurrency wallet. You can use it as a store of value. You can use it to transfer money to other people. Just like you would PayPal them money, you can send them your cryptocurrency. You can use it as utility tokens to pay for services. So there can be services online that you pay for with these tokens. You can use cryptocurrencies that way. Economists endlessly debate, well, what is cryptocurrency? Is it money? Is it equity? Is it stock? Is it a utility token? And the answer is, I don't know, it's sort of all those mushed together. And they say it's none of the above. It's this new thing called a cryptocurrency. It's beautiful. And then you can do other things. We are starting to see people add on other features now, like strong anonymity, where you don't know who has a given wallet, or strong transparency, so that banks can do know your customer things, or microtransactions. If I have to pay a couple of dollars for each of my transactions, there's uses for it. But if I could pay 1/1000th of a cent, there's more uses for it. You could start talking about maybe paying 1/1000th of a cent for reading papers behind a paywall rather than having to put in your credit card and buy a $30 paper. You could talk about all sorts of interesting things where you do micropayments, which would be enabled if you could do 1/1000th of a cent per transaction or smaller. So these are some of the things that we can do with cryptocurrencies. They were the first generation. They continue to evolve even now. But people said, you know what? This Bitcoin thing was really cool. It's doing a cryptocurrency. In order to do the cryptocurrency, it has to remember all these transactions. It has this ledger that remembers them all. It's this blockchain that remembers them all. But wait a second. It's a computer. It's just ones and zeros. We don't have to limit ourselves to just remembering things about coins. We could put other stuff in that ledger, and it would be just as good. It'd be just as trustworthy. And so we got the second generation of DLTs, which was, well, let's not just have a money. Let's have a file system in some sense. Kind of expensive, so little tiny files. But the important thing is that nobody can change it when they shouldn't. And if I think there's a piece of information there and you look at it, you are guaranteed to see the same thing. We have a shared view of what's going on. Everybody knows that everybody knows about it. The rules are enforced by the entire community. No one person could delete things. No one person could add things by themselves in an illegal way. This is a powerful concept. And so the second generation of DLTs was saying we can go beyond money. We can go beyond cryptocurrencies. We can store information in these things. You could store ownership of something like land. Why is it important to put a deed, or at least a hash of a deed, into a ledger like this? Because if I try to sell my property to two different people, I could hand them each a Xerox of the deed, but when you try to buy it from one of them, you want to make sure that no one else has it. You want to do a check on who owns it. But if you have a ledger, you just look in the ledger and you're guaranteed to see the same thing everyone else sees. So you're guaranteed that the whole world is seeing who owns this land right now. We're all seeing the same picture. That's a powerful concept. Very powerful. And you could do other assets, not just land, but any kind of asset. You could have digital assets in this ledger. And you have this guaranteed shared view. If you can do that, you can do revocation. For example, maybe the DMV issues me a driver's license. I could put my driver's license in the ledger. And maybe that's not good for privacy. I could put a hash of my driver's license in the ledger. That's a scrambled version of it that you can't understand. What good would that do? It would do a lot of good if it allows the DMV to revoke it. Because if I go to you and I want to convince you that I have a driver's license, it's not good enough for me to just show you some file signed by the DMV that says I had a driver's license. Because maybe I got into some accidents and they pulled my driver's license. Maybe they revoked it. They canceled it. So we want to be able to do revocation. We want the DMV to be able to revoke my driver's license. So what you could do is have a ledger where the DMV has the rights to delete your driver's license, but nobody else does. Or maybe the DMV has the right and you have the right, but no one else has the right to delete your driver's license. Then when you want to prove to someone you have the driver's license, you give them the file, they look at the hash and they look in the ledger and they see if it's still there, and if it's still there, they know you still have a valid driver's license. So we can do revocation. You can do audit logs. Stick information in there that some government agency wants to look at, or that some accountant wants to look at it, and have a guarantee that it hasn't changed over time. And we can do stuff with identity and your attributes, and we can do metadata for things like medical applications. All of these things with the second generation, and there's a lot of interest right now, it's still embryonic, of how to use ledgers. But that's just the second generation. Then we had the third generation, which was, well, if I'm going to be able to store my land in the ledger, and you're able to store your money in the ledger, maybe we could do a swap. Maybe I could give you my land in exchange for your money. Now, we could just email it. But here's the problem. You email me your money and then you never hear from me again because I run off and I don't give you the land. Or I email you the land but you never send me the money. That would be bad. So what you do is you have a trusted third party. We both give our thing to the trusted third party, then they swap it and give it back to us. But with a smart contract, you can actually have a computer program being run by the entire community, and they can all agree on whether or not the swap happens. And you can prevent cheating. An incredibly powerful idea. Let's have little programs that are running. So you can do sales like I just talked about. You can do agreements with non-repudiation. If you and I want to sign a contract, I can make sure that I sign it and that you sign it and we both get both signatures, and I can eliminate the possibility that I signed it, handed you my signature, and then you just put it in your pocket and kept it. And then a year from now you could lie and say, yeah, I signed it too, and enforce it. Or a year from now you could lie and say, I never saw it, and not enforce it. That would be bad. With smart contracts, you could prevent that. There's lots of things you can do, including distributed applications, DAOs, distributed organizations, all sorts of cool things. So those are the three generations we started with. First, let's put some money in our ledgers. Well, if we're going to do that, let's put other information like assets in our ledgers. Well, if we're going to have money and assets, then let us be able to trade them with each other and do smart contracts. But if we can do that, that raises the question, should we do a fourth generation? If we have money and we have assets and we're able to swap money for assets with sales, then how do we get matched up? We need markets. We need some way that the sellers and the buyers can get matched up with each other, and so they can do the buying and selling. And so with the markets, we can complete it. This does everything then, but you have to have fairness. We need to know that we're going to have fairness in how we match them up. If you have the fairness, then you can have markets. I'm calling that the fourth generation, but it's more than just what you would think of as markets. It includes things like video games. We need fairness in a video game. In some MMO, if you pick up an object and I pick up the object at the same time, we need to make sure that I can't cheat and make it seem like I picked it up first when really you picked it up first. This is the goal here, is we want to be able to not have people cheat and influence what the order that we agree on is going to be. But if you have that, you can do games, you can do stock markets. I don't really think we're going to do the New York Stock Exchange this way, but you could also do dark pools, which are like little tiny stock markets run by a small number of banks. There it is absolutely a useful thing, because they don't really trust each other individually, but they would trust that a big group of each other wouldn't do something bad. It's the perfect situation. You can do games, you could do auctions, you could do something like an eBay or an Amazon. You could do something where first to file matters. You could set up a patent office. You could set up an office selling domain names. Anything like that where it matters who was there first. So those are the four generations. You'll notice that as I've been going along, the four generations happened in that order, but all four of them continue to evolve. And we're getting new use cases, new business cases of how to use these things in all four of these applications, and that the things that we need in many of these cases are coming down to fairness and speed. And as we more and more grow up and mature and become real markets where we're using lots of money, security becomes increasingly important. Resilience to DDoS attacks, that sort of thing. So I've told you what Hashgraph can accomplish. I've told you the history of how ledgers have evolved and how they're continuing to evolve rapidly. How does the Hashgraph actually work internally? What's the algorithm that it uses? Because it's very different from proof of work. It's very different from leader-based. It's very different from simulated economies, which you may have heard called proof of stake or called DAG-based. Very different from those. I don't like those terms because, well, I can do proof of stake and I use a DAG, but I'm not at all like the systems that are simulating an economy. Instead, we're going to do something totally different. In fact, really, it goes back to the way it worked 35 years ago, except those systems were so slow you could never use them. So I'm just going to tell you in about 2 minutes how it works. Here's the whole algorithm in 2 minutes. And if you don't like math, you only have to suffer for 2 minutes. We want speed, right? So here's the idea. Alice has that red envelope. She has created a transaction. She wants everybody to know it. So she tells someone totally randomly. This is about the simplest algorithm I can imagine. And now Dave knows it too. 2 people know it. And then each of them tells someone randomly. Now 4 people know it. And then each of them tells someone that they pick at random. Now 8 people know it. It explodes outwards exponentially fast, and soon everybody knows it. And if you attack one of these computers and shut it down, doesn't matter. It'll still just spread out to everybody else that it wasn't being attacked. There's no one computer that's a bottleneck. And there's no one computer that has to call everybody up one after another and tell them. Alice doesn't have to call each person and tell them individually. She just tells someone and then tells someone else, and then they're telling someone else, and it just explodes.
Is it random out of the pool of people that don't know yet? Yeah.
Ha! Almost. Actually, what you do is you call somebody, but then you make sure you only tell them things they don't know. And so what will usually happen is you're going to have a whole bunch of information. When you call a random person, some of it they'll know, some of it they won't. And there's really clever ways to make sure you don't tell them something they already know. That's a really good question.
Well, I have a dumb question.
That's good too.
What if you attack the only person that knows, in this case Alice? Then no one will know.
If an attacker shuts down your computer, you are not going to be able to bid in our stock market. You are not going to be able to play our game.
So how is that fair?
Well, that's not a failure in the consensus algorithm, that's life. That's the truth. But what doesn't happen is the whole network shuts down. And with something like the leader-based systems, the whole network shuts down if they attack just the right person and keep following the leader. So let's be clear here. Nothing is 100% secure. If you have a third of the people being evil, they can do terrible things and corrupt the network. If you have a botnet that can shut down a third of the network, they can freeze the whole network. If there is an earthquake that chops off a third of our people, then the whole network freezes. Nothing can help you with these things. But nothing less than a third is going to hurt you. And that's the point. Yes?
What incentivizes these individuals to gossip about each other?
This is a layer above the consensus protocol. So one answer might be maybe it's a permission network, and the only way you get to be part of the permission network is if you're doing the gossiping because you learn information. Another might be you're doing something that's proof of stake and you get paid to be a miner. Another might be that you and a few of your friends are playing a video game, and unless you're doing the mining, then you don't get to play the video game. There's lots of different answers. That's all at a layer above the Hashgraph layer. And I know. We're going to have a long time for questions. 90% of the questions are going to be, so what do we do about this public network and this cryptocurrency and this, those sorts of things? And the answer is it's all a layer above Hashgraph. And I'm sorry I don't have an answer, but I'm talking about how the Hashgraph works. Yes?
But if Dave is targeted and his envelope turns blue, then it's going to be a multiplied blue effect across half the network.
If Dave is attacked,
Yeah.
Oh, you're saying in the very first step. Alice calls Dave, notices he's not talking, and then she just calls someone else at random. In fact, I said her second call was to Gina. If Dave doesn't talk to her, she still talks to Gina.
Dave talks differently and turns the message blue.
Good question. What about digital? We have digital signatures. Nobody can corrupt a message. We have digital signatures. In fact, we're also going to use cryptographic hashes to tie everything together. There are huge classes of lies that you just can't tell in this system. Mostly all you can do is just go silent, or set up firewalls or something to break the network, or DDoS somebody. But you can't really lie. If I tell you that Alice gave me this message, since she signed it, you know it came from Alice. And replay attacks don't happen. There's all sorts of things that are just completely impossible unless you break the crypto. And I use strong crypto, really strong, maybe more strong than I need to. Yes?
Sorry, this is a stupid question, but if you check with another node to see if it has the information, and if it already does, you check another one, isn't the last step of this process going to be every node sending a message to every other node in the system? And if so, what's the efficiency gain that you get from the initial propagation using this random system?
Excellent question. If I understand it correctly, hold 1 second, that's the next slide. If I understand it correctly. And if I don't, let me know after the next slide. So what I said is that if Alice wants to talk, the fastest way that computer science knows for her to get it out on the internet is a gossip protocol. This is faster than a message tree because you're resilient to one node going down. And it's much faster than Alice talking to everybody individually. The fastest, most resilient way we know to get the message out in computer science would be a gossip protocol, which is the simplest possible thing. Just talk to people at random. It's about as simple as you can get. Now here's a question. What if Bob and Carol both want to send out a transaction at the same time? Which is starting to get to what you were talking about. You could say, we're going to make them take turns. We'll have some mechanism that decides who goes first. We'll let theirs propagate to everybody, and then we'll let the other person's. Databases sometimes do this in two-phase commit. There's locks involved. Leader-based systems implicitly do this. Any system where they have to take turns has a host of problems that slows you down. What would be the fastest way to do it? Just do it. They both call someone at random and give them a message. And then they call someone at random and give them their message. And then they call someone at random and give them their message. And exponentially fast, everybody has both of them. In a real system, everybody is creating transactions all the time. So you have an enormous flood of transactions going out all the time. When I call you, there's always going to be a few messages you haven't heard yet, and you'll get those. And so it's not like we're taking turns. We don't wait till one message gets to the whole network and then we start on the next message. We're just constantly talking to each other, spreading our messages as they're being created.
How do you prevent double spending?
Aha! To prevent double spending, you have to know an order on your transactions. And the ordering we haven't got to yet. In fact, and that's an excellent question, look at the colors on Alice and Bob. Alice received red, then blue, then green. Bob received red, then green, then blue. They cannot look at the order at which they received them. So to be clear, a gossip protocol is the fastest, most resilient way to get the information out, but it does not give you a consensus order. We've only just begun. We don't have a consensus order yet. So lots of people start with this, and then they say, now let's talk about consensus. But I don't want to talk about consensus. I want to talk about something else. I want to add a tiny little bit of information to each of these messages, like 1% bigger, just a few more bytes to each message. That's all I'm going to add, is a little tiny bit of information to each message, and that's going to be enough for you to see an incredible history of how we've all talked to each other, which is weird. And then we're going to get consensus for free. You will not have to talk to anyone, and you'll have perfect consensus with math guarantees that you're right. That's weird. That's crazy. So let's talk about this. We all have these messages, and you know, I just showed this animation of everyone talking to each other. Let's draw a diagram of it. No one ever draws diagrams of this. I want to draw a diagram of it. So here's a network with just 3 people, Alice, Bob, and Carol. Time goes uphill. You see the 3 circles at the bottom are Alice, Bob, and Carol. Those are just the 3 at the bottom. Each of these circles then, above that, represents an event of somebody gossiping to someone else. So look at the top circle in the whole thing. That's the last event that I have in this diagram, and it is in the Bob column. And it has a line going down to a circle in the Carol column. That top circle represents the event where Carol called Bob and told him everything she knows. All the messages she knows she gave to Bob. This diagram is a way of seeing the whole history. If you look at this diagram, you can see how we talk to each other and in what order we talk to each other. And in fact, if you told me there was some information in Alice's circle at the very bottom there, I could just follow the lines and see how the information flowed through the network. It's really kind of cool. And if you told me there was something in Carol's circle at the bottom, I could see how it flowed. And for any given person, I could tell you which of the 2 messages they got first. You can just watch how everything flows through the network from this diagram. It's a really cool diagram. Nobody ever draws these diagrams, but this is a diagram you could draw that would show you the whole history of gossip. Now, we can gossip about transactions. We could gossip about identities. We could gossip about information that we find interesting. But what if we were to gossip about gossip? What if we were to be gossiping what we know about this very picture? What if we were to do gossip about gossip? In other words, when I call you, I give you everything I know. What I mean is I give you all the pieces of this very picture that I know. That's weird, very recursive, self-referential. We are going to gossip about the picture where the picture is the record of how we gossiped. Bizarre. But we're going to do that. So each of these circles now is actually going to be a little data structure in our memory that is the message that we're sending people. Now we do want to have some transactions, so you'll put the transactions inside the circles. But in addition to a circle having to have the transaction, it will also remember 2 lines going down from itself. The thick line for what column it's in and the thin line for who was talking to that person. Just 2 lines, 2 pointers, 2 hashes. We're building a graph held together with hashes. In math, this is called a graph. It's held together with hashes, so we call it a hash graph. So the hash graph is the history of how we've all talked to each other. But all I have to do is send you the transactions I was going to be sending you anyway, digitally signing them, sending you timestamps, all the stuff I would have been doing anyway, plus 2 hashes. That's it. Each message just has to be bigger by 2 hashes. And in fact, for various reasons, I can compress each of those hashes down to 1 or 2 bytes, and I'm fine. I still have total security. So we started with gossip. That's the fastest way to get your transactions out. We added a tiny bit of overhead, and for free, we got the whole hash graph that shows the entire history of how we've all talked to each other. And now we know what each other knows. I know what you know. And I know what you know about what she knows. And not only that, I know when you learned about what you know about what she knows about when he learned this thing from him. I know it all.
Wait, so do you also need to include a timestamp in that?
We're doing that. Each of those circles has a timestamp in it. You got it.
That's a massive amount of information changing hands. I mean,
it seems like an enormous amount of information, but wait. If we're all creating transactions, then these circles have the transactions in them. They would have had to anyway. And they have signatures, but we would have had to do that anyway. And they have timestamps. Even Bitcoin has timestamps. So if we just looked at a system that was purely trying to get the transactions out and not worrying about consensus at all, you would still have to send the transactions, the timestamps, and the signatures. This thing is sending exactly that plus 2 hashes in each message. And the hash can each be compressed down to 1 or 2 bytes. So it turns out to be a tiny bit of additional information on top of what we were already sending anyway. That's what's so weird here.
So you're not sending the history of information, just two hashes that's kind of
That's it.
relates, kind of, okay.
How does that work? Why don't I have to send the whole history? I had to send you these transactions, so you had all the transactions. I had to send you these, I had to send you these, I had to send you these. So when I send you that top circle, I don't have to send you all these circles, you already have them. All I have to do is send you this little line here that tells you which circle it connects to. So you think you're getting this enormous history, but you already have all those parts of the history. All I need to do is connect it to two things. So you just have two hashes, that's it. So the amount that I'm sending you is a tiny bit beyond what you would have had to send anyway just to get the transactions out there. But we now have this beautiful picture of history. So it's cheap, almost for free. We still don't have consensus order though. There's still no consensus here. If you look at that picture, you can't put the circles in order yet. But here's the weird thing. I had to send you the transactions, the signatures, and the timestamps anyway. I've sent you a tiny bit of information in addition, which gave you this entire hash graph, which let me know what everybody was thinking and when they knew it and what they knew. Now I'm going to go to the shelf and get one of those 35-year-old algorithms that were so beautiful mathematically. Really strong proofs, asynchronous Byzantine security, the strongest known algorithms, but they involved voting, sending votes over the internet. And with so many votes, it just collapses under its own weight. It was too slow. To my knowledge, no one has ever actually deployed in the real world a system using these things, these voting systems. But what we could do here is I could say, I know what you know. I know everything about what you know. In fact, if we were running one of those old algorithms, I know exactly how you would vote. So don't bother voting. I'll just pretend that you voted. I'll just pretend that you sent me a vote. And so we're going to run one of these old voting algorithms, but with no votes. We're going to do virtual voting. By doing virtual voting, what I mean is that we're essentially running old algorithms. They're tweaked a little bit. They're actually slightly different, but it's basically running these 35-year-old algorithms that have these wonderful math proofs. The only downside of the voting algorithms is because they have lots of votes and receipts. But we're doing it with no votes and no receipts. And so purely in my mind, I run one of these algorithms and I know the consensus order. So practically, what does this mean? It means that whenever I need to get a transaction, if you've created a transaction, it will get to me very fast because we're using gossip. Doesn't have to go through a leader. Don't have to take turns. Don't have to solve a math problem in a proof of work system. I'm going to get your transaction really fast. I will have to pay for maybe 1% more bandwidth to get it because you're going to throw in the two hashes. And then, after I get a few more transactions, I will just know the order of this one. I don't have to talk to people about the consensus. I don't have to talk to a leader. There's no one person in charge. It's purely internal. I can just see what the consensus is by virtually running one of these old algorithms, but not running it for real. And so one of these circles has these things in it. It has transactions in it. It has a timestamp. It's signed by its creator and it has the two hashes, and even those can be compressed because I'm always sending you the hash of an object you already have in memory, and you don't have very many objects in memory, so it doesn't take very much effort to tell you what hash I'm thinking of. And that's it. Hashgraph works by gossip about gossip with virtual voting. It's bizarre. This gossip about gossip thing is weirdly self-referential, but you get all the decades worth of math proofs all apply. It's asynchronous Byzantine, it's fair, and the speed is as good as you're going to get. Gossip is as fast as you're going to get. You're just paying this tiny penalty of 2 hashes. And there's no communication at all for the consensus part. You get that for free. But please, let me have questions. Yes?
2 really quick questions. So I'm assuming the sending the hashes is how you get around a node getting information and then having to recheck the rest of the system because it knows which nodes have already passed along that information from one to the other. How does the number of hashes that you have to send scale with the number of nodes in the system? So if you have 1,000 nodes instead of 3, do you have to send some function of that nodal system in terms of hashes, and does that add to the actual data that's being transferred in each transaction?
It does not. Now let me rephrase your question. The word node, I hate this. Circles are called nodes and computers are called nodes in these 2 communities. And now we're in the intersection of the 2 communities. But you're talking about computers. I understand that. I usually call them full nodes, and I don't call circles nodes for the very reason of this. The question was, do I have to send more hashes? Here's the answer. If you have a good flow of transactions so that each of the computers, each of the full nodes is putting some transactions into each event, then the overhead is constant no matter how many people you have. The overhead in bytes that you have to send is constant. You end up having to have bandwidth proportional to the number of transactions per second you want to handle. That's constant. That's throughput. Then you have latency. Latency is logarithmic in the number of nodes because of what we just saw several slides ago. It's exponentially fast. Well, exponentially fast, invert that, you have logarithmic. So if I have 1,000 nodes, I'm probably going to have to talk about 10 times before my message gets to everybody. If I have 1,000,000 computers, I'm going to have to talk 20 times. If I have 1 billion computers, I'm going to have to talk 30 times. It's logarithmic. And again, that's the best you can do with the internet. Yes?
I actually do want to ask the complexity part. So you mentioned it's logarithmic. Then can it apply to a public ledger, like over massive scale, like Bitcoin, Ethereum?
The answer is yes, you could build a public ledger on Hashgraph with one shard, which I think is what you're asking. But if I had more than 1,000 nodes, I wouldn't waste it all on one shard. I'd get more shards and get even more speed. So let me just mention sharding really briefly here, and then I'll continue with your question. Just like computers have single processors, or you can get a graphics card that has 1,000 processors in it, same thing with shards. You can have a ledger where every computer knows everything. Every computer gets every transaction. But of course, you're limited by how many transactions per second you have the bandwidth for. If my computer can only get 500,000 transactions per second, then the entire network is limited to 500,000 transactions per second, which is actually a big number. But for some applications, you want millions or billions of transactions per second. How do you fix that? Well, you don't make every computer see every transaction. What you do is you divide your computers up into clusters, and within a cluster, they all see the same transactions, but each transaction only goes to one cluster, only goes to several clusters. These clusters are called shards. That comes from the database world, where databases put data on just some computers. So if you wanted a big system with 1 billion, I wouldn't waste them all on one shard. I would make a whole bunch of shards that are each 100 or 1,000 because you get all the benefits of sharding. Hashgraph would work fine in that big system, but I would actually build a sharded system. Now, the bigger question you're asking is, how do we go about doing a public ledger, and how do we go about doing sharding? And the answer is there's many ways to do that on top of Hashgraph. And you could use Hashgraph as a building block to build a sharded system or a ledger, public ledger, in many different ways. We haven't published one yet. So don't ask me the algorithm. There is no algorithm we've published. But we may do that in the future. And right now, what I'm describing to you is a building block that makes a single shard really fast. Yes?
Since we're in a business school,
Yes.
I would ask more business-related questions.
Excellent.
So I understand that there is a company behind the Hashgraph, where the company
Yes.
is trying to kind of monetize the value of the Hashgraph.
Yes.
When you are going to pitch the technology to enterprises,
Yes.
do you position yourself as a blockchain-like technology that has
Yes.
some competitiveness or
Yes.
kind of edge over blockchain? Or you are kind of trying to stand out from the crowd of technologies out there? Because from my understanding, blockchain is still in early days of the development.
Right.
So how would a company be willing to understand that you are more kind of
Yes.
advantageous in front of a blockchain if they
Yes.
cannot understand the blockchain itself at this particular moment?
Yes. So oddly enough, we have to educate people, but this happens. So let me tell you, for example, the credit union industry. There's 6,000 credit unions in North America. They created an organization called CU Ledger, Credit Union Ledger. The purpose of CU Ledger is to have a single ledger, they were calling it a blockchain, that would store information that the credit unions want to share with each other, and it's this whole deal that we talked about. They want it to be private, so people outside the credit unions can't see it, but the credit unions themselves will see it. No credit union trusts a single credit union, but you can bet that of the 6,000, probably no 1/3 of them are going to be evil. So it's the traditional permissioned ledger situation. They said, we want to build a blockchain. Again, people use the word blockchain to refer to all DLTs, including us. So in that sense, we are a blockchain. We talked to them. Actually, they called us. They'd heard of us, and they called us. And then they looked at other ones, like Hyperledger. They looked at a number of competitors, and they implemented in-house. You know, our stuff's been on our website for a year and a half. You just download it and play with it. And you can build little apps on top of it and see how they work. They tried that. They were very impressed, and they chose us over these other ones, like Hyperledger. And the reason that they chose us was it's fast, fair, and secure. They actually didn't care a whole lot about fairness. As I said, some of these early applications don't need it. Something like a game or a stock market would need it. But they cared about fast and secure. And honestly, what they cared about the most was fast. They wanted this incredible speed, which many of the public ledgers wouldn't give them. But they were also somewhat concerned about the security. If you try to get speed by going to a leader-based system, then you've opened yourself up to DDoS attacks that can be really bad.
So basically, your target market as of now is companies who want to implement blockchain,
Yes.
and you're winning deals over blockchain as a
Yes.
faster, more
Yes.
reliable, and so on and so forth.
That's right. Right. So every time we talk to a company, we talk to their blockchain division. And I don't complain. I mean, that is one of the definitions of blockchain means DLT. And we're a DLT, so we're a blockchain. But what we say is, look at the speed that we have, look at the security we have, and look at provable, mathematically proven security, and look at the fairness that we have. And so we have lots of customers in the pipeline that are they're very excited about this. And oddly, it's the speed that seems to get people the most excited. But then when we talk to them enough, they start to realize, yeah, security matters too.
Along those lines, I actually have two questions. The first is, can you talk about what's next for Hashgraph, maybe in the next 6 months or a year, any milestones that are top of mind? And then the second is, forgive me being a noob here, but if this is such, I mean, it's not like a new technology, the gossip-based protocol, so why haven't like Ethereum or other blockchains implemented that, from the get-go?
Oh, I'll answer the second one first. Okay. Gossip is really old. Gossip about gossip is unprecedented and very weird. Okay. Not the kind of thing you'd think of. Right. And then virtual voting, taking one of those 30-year-old algorithms and trying to apply it on a gossip about gossip system, just bizarre. Okay. That's the short answer for that. It's just strange. Though I will say, every time I've talked to a mathematician, they say, oh, well, that would work. Huh, never thought of that. Right, it's kind of weird, but when you see it, you say, well, yeah, that would work. I understand. They don't even have to go through the proof. But we do have a proof with lemmas and theorems and stuff. Yeah, a real proof. Yeah, and I actually forgot the first half of your question. What was the first half?
What's next for Hashgraph?
Oh, yeah. Yeah, I won't answer that part. So Swirlds Incorporated is selling these permissioned ledgers. We're getting amazing traction. We plan to continue to expand that to add more features. And we will eventually add sharding and all sorts of things. As for the public side, we haven't said anything yet. We have not announced algorithms for that. Hashgraph by itself is a good foundation for a public ledger, but is not a public ledger because you have to say, how are you going to do sharding? How are you going to do stake? How are you going to do lots of different things, the smart contracts? All those pieces have to be said. So my short answer would just be stay tuned. Okay. Yes?
I guess I have two questions. So on the permissioned ledger side, for example, for a game,
yes.
Is the value proposition that for a game like World of Warcraft or something, is it sort of a cost-saving measure where they wouldn't have to host a game sent in a centralized way, which presumably costs money? They could distribute it amongst their users?
This changes the entire economic model. You can imagine users who don't have to pay for a server because there is no server, it's just their computer while they're playing. Right now, some kid has to pay Microsoft $10 a month to play Minecraft, and they can only have 11 kids playing at a time. But this could be free, and you could have 1 million kids playing at a time. So it's a different economic model. How about an indie game developer that would love to do an MMO, but can't afford the big servers? They don't have to.
But for that, he would need access to a public version.
No. So an MMO can actually be just the players themselves running it. It doesn't have to be public. Probably what you would actually do for an MMO, as I think about it, is that you would have part of it being public and part of it being a whole bunch of little privates. And they would all be connecting to it. It'd be almost like side chains. But it depends on how you want to do it. But if you wanted to, you could actually start with purely private if you wanted to.
Okay. And then I guess my second question is this enough, this framework enough for someone way smarter than me to use the math and change the consensus algorithm underlying Bitcoin or Ethereum on their own, or do they need more information?
Good question. No, it is enough. And furthermore, these guys are smart. All these systems like Hyperledger is an enormously complicated stack of technologies, and they built it modular. It's plug and play. And guess what the very bottom module does? Just the consensus part. And so absolutely, we're talking about building plugins that will do that. Absolutely. And so these big stacks that people are building, they're doing the right thing, which is to make them modular. And so then you can have all these different consensus algorithms at the bottom. You just plug ours in, which is a good thing. Yeah. Which I guess answers my question about the future, which I wasn't going to answer. Yes?
Pardon my limited understanding of the technology. Would you mind sharing how for conventional blockchains where you've got an immutable chain of blocks, I understand that there's a hash that's associated with the previous block that has to get matched with the new block, and there's a cryptographic kind of equation that goes into solving that.
Very good.
How is that different to this?
Yes.
And also my second question is, how do you get enough computers and people on board? Do you need to have the user base alive before this kind of actually starts to work?
Again, I'll start with the second question. For the user base, we just got 6,000 credit unions that'll be using it because they benefit from it. Okay, so that's not a problem. For permission network, it's whoever wanted to be playing it. If you released a game, then you would say, well, whoever wants to play the game, you invite your friends, and those are the people playing it. That's not a problem. If you want to talk about a public ledger, that's an entirely separate question. There's a whole bunch of issues that arise. And so all of those need to be solved. And Hashgraph is a beautiful building block to use in such a system, but I haven't published such a system, so I can't talk about details of it. But I think Hashgraph is a nice... It's good to use Hashgraph for the consensus part of that system, but a public ledger is much bigger than just a consensus algorithm. Right. And then the first half of your question, which I also forgot.
How's it different to a conventional blockchain where you're matching the hashes from one block to another?
Got it. So the short answer is a blockchain is a chain of blocks, and a hash graph is a graph held together with hashes. Here's the less short answer. In a blockchain, and when you say blockchain, I'm gathering that you mean proof of work. You're not talking about one of the leader-based systems. You're talking about proof of work. In a proof of work system, the way it works is that you have a chain of blocks, each of which has the hash of the previous one, so nobody can go back and change something in the history. It makes it immutable. And then, to put the next block on, somebody will come along and put the next block on. That's great. The problem is if two people put the same next block on, then we as a community have to chop off one of them and only accept the other one. And we do that by voting with our feet. We decide which of the two to expand. You always try to extend the one that's longer. And then eventually it's so much longer that we just throw away this one and no one ever bothers with it. That's how it works. The problem with that is that if we were forking this way too often, we would get new forks before we finish chopping off the old fork, and the whole system would collapse. We'd keep sprouting new forks all the time. So we have to slow it down. So how do we slow it down? We do proof of work. In a proof of work system, the whole purpose of the proof of work is to make it run slower. That's interesting. I don't have a part of my engine in my car whose purpose is to make my car run slower. But that's the whole point of proof of work, is to make sure that we're only adding a new block every 10 minutes, or some of the newer ones would be much faster, but to make sure it's slow enough that the community as a whole will have time to figure out which of the chains is longer and always go with the longer fork. To do that, you have to solve a math problem. The math problem does involve taking a hash and trying to find one that will have certain zeros and so on. But it doesn't even matter what you do for your math problem. The point is, it's a useless math problem, but it's really hard to solve, so you need a supercomputer and lots of electricity. Problem. Anytime that you need a supercomputer and lots of electricity and there's economies of scale, you're going to have minor consolidation. Fewer and fewer people are going to have that supercomputer. And if it uses lots of electricity, everybody's going to move to where the electricity is cheap. And you can have geographic consolidation. And once you've got minor consolidation and geographic consolidation, then our beautiful trust model maybe is not quite as trustworthy. If we all live in one spot and the government of that spot nationalizes all our mining rigs and makes them start extending the shorter branches, then they've destroyed the entire system. So that's how the blockchain works. For us, you don't have a chain. You just have that picture I showed with all the circles with lines. And anybody who wants to add a new circle does it. In fact, typically the experiments I run, each individual computer is adding 10 new circles every second. So it's like a miner in Bitcoin mining 10 blocks a second. Every single miner mining 10 new blocks a second. In blockchain that wouldn't work because it'd be too fast. We wouldn't be able to chop off these forks. But in Hashgraph, we like forks. Nothing ever gets chopped off, so there's no problem.
So is it the overlay of this voting algorithm that kind of
Yes.
validates that there's not different kind of information?
That's it. In fact, that goes back to the question you had asked earlier too. In a blockchain, it's easy to put them in order. It's just the order of the chain. But in this system, maybe it isn't so obvious. Oh, there's the graph. That graph there, it isn't obvious what order to put the circles in. But because the graph represents the history of how we talked, I know enough to run in my head one of those old voting algorithms, and I can put every single circle in order. And so in my head, I do actually put every single circle in order. That puts all of my transactions in an exact order that I know everybody agrees on. And then if you double spend, I know which of the two stores got it first and which one got it second, and we say the money actually went to the first store and not the second. So all the problems go away. So we get beautiful advantages by having a graph rather than a chain, but then you say, well, how do you get consensus? And we do that by doing the virtual voting. But you can only do the virtual voting because I have this history of what we all know and how we talk to each other. And the reason I have the history is because I did gossip about gossip. I did a hash graph. And that is how this is different from other systems that use a graph. There's a bunch of systems out there that draw pictures that look like that picture. But their picture doesn't represent a history of how we talked to each other. So they couldn't do virtual voting. So they couldn't get all the advantages of that. Yes?
Sure. So with proof of work based blockchains,
yes,
they really, for a bad actor to kind of corrupt the system, you need to have 51% of the hash power, they say, which is a really high bar.
34, yes.
I thought it was 51 because they always
Yes,
call it
that's
the
a common
51.
thought.
Okay, so
It's
that's,
actually 34.
so that was basically the point of my question, because earlier you said it's 1/3 with this system. I was
It
wondering
is.
if there's a difference between blockchain and the graph system.
No. So there are lots of people who are aware that Bitcoin is a 34% system because there's math theorems that say that every system is a 34% system. I should have brought the pictures. By the way, I have a video on our website of me giving a talk at Berkeley at the Crypto Economics Conference. And I go through this. And in fact, at that same conference, one of the earlier speakers just casually mentioned, and of course, 1/3 can attack Bitcoin. So apparently it's common knowledge among some people, but other people talk about 51. The right way to say things is there are 51% attacks on Bitcoin. But there's also 34% attacks if we're assuming that there are things like firewalls in the world. And that's what we have to talk about, is if you're assuming that there are things like firewalls in the world, then 34% is enough. Here's how it works. Imagine that we are all computers and that we are evenly split between these three sections of the room. This room is conveniently split into three sections. So 1/3 of us live over here, 1/3 of us live here, and 1/3 of us live here. And we will furthermore assume that the people in the middle are all malicious and evil and bad people. I'm sorry. But you guys are good, and you guys are good. Now imagine that there is a firewall around our country over here that is around these 1/3 of the people. So I'm going to build a firewall around this 1/3 of the room, and then I am going to be a malicious person, and I'm going to turn off the firewall. In other words, I'm going to shut down all traffic between this 1/3 of the room and this 2/3 of the room. Now, if you have a simple Bitcoin with no partition detector, then the attacker has already won. What's going to happen is you guys will keep talking to each other. You won't talk to them because you can't. And as you're talking to each other, you'll keep trying to mine, and you'll keep adding new blocks on top of the chain. It'll be running at 1/3 of the speed as what it usually runs, but you'll notice that it's working, and you'll build your chain. You guys will do the same thing, adding different blocks and adding them to the chain. And you'll notice that you're running at 2/3 your normal speed, but you're still running. That is bad. Because your chain can get 6 long, or 12 long, or 1,000,000 long. Yours can get 6 longer, have 6 confirmations, or 12 confirmations, or 1,000,000 confirmations. And now we have 2 contradictory histories, 2 contradictory chains. So that is bad. And if I have a satellite phone, or if I am colluding with the firewall person and they let my messages through, I can double spend. I could spend my coin on this side and spend my coin on this side, wait for 6 confirmations and have the store give me my product, wait for 6 confirmations and have the store give me my product, and now I have 2 products for the price of 1. I have cheated. That is for a simple Bitcoin with no partition detector. So then you say, wait, why don't we do this? why don't we say that we will just freeze if we notice that a third of the world has gone silent mysteriously and not talked to us. Okay? Oh, well then we don't even need the firewall. I said these middle third are malicious, they just turn off the computers. And then you guys will say, oh, a third of the world has gone silent, and you'll all freeze, and the whole network freezes forever. Okay, so not that. Why don't we have a partition detector that says, if more than a third of the world goes silent, then we'll just freeze. Now, it's okay for this firewall, because what happens is you guys will freeze, but you guys will say, well, we have a full 2/3 still talking to each other, we'll keep going. And so now I can't double spend. All is well. Except these guys are malicious. And you guys are colluding with the person who made the firewall, and the firewall lets your messages through. Now you guys are getting messages from 2/3 of the world, you and them. And you guys are getting messages from 2/3 of the world, you and them. You guys are sending your messages both ways, and they get through the firewall, but you guys aren't able to get through the firewall. Now our partition detector is totally happy. It says, hey, 2/3 of the world is communicating with me. I'm going to keep going. And so you guys get your own chain, and you guys get your own chain, and they're different, and I can double spend. And these malicious people who are talking to both sides can easily double spend. That's bad. So you could say something about, okay, we're not just going to do partition detectors based on who's talking to me. We're actually going to count how many blocks get added. Well, we still have a problem in that these guys are going to be adding blocks on both chains, but at least they're running at half the speed. So now your partition detector has to somehow guess how fast each person by themselves is producing blocks. But any given computer isn't producing blocks very fast anyway. They don't mine very often. So it's going to be really hard to notice that he now seems to be going half his normal speed rather than his full normal speed, because any one computer mines pretty slowly anyway. And so I'm definitely going to be able to double spend. And so no matter how you try to build your partition detector, you end up finding that either the attackers can double spend, or the attackers can shut down the entire network forever. One or the other. This is not surprising, because we have 35 years of math proofs all saying that you will always be able to attack if you have a third of the people who are malicious and you have a firewall. You will always be able to either freeze everybody forever or force a false consensus. One or the other. Yes?
Is a 33% or 34% plus firewall attack more feasible than a 50%? In other words, is the cost of building a firewall lower than the additional 20%?
Oh, it depends.
Yeah, I'm just curious. I have no idea how you would go about doing that. So is it sort of like, it's not necessarily true that because a system is vulnerable to this kind of a 33% attack, that it's less secure than what people kind of conceptualize as it being secure against only a 51 or 51+% attack. Okay,
so you're asking two different questions. One was somebody said, I heard 51, I didn't think it was 34. And I'm just saying, well, actually, mathematically, it's 34. To some degree, the two numbers are so close, it doesn't matter a whole lot. But you're also saying, in practice, would there ever be such a firewall? Guess what? There happens to be a cryptocurrency that is concentrated in a country that happens to have a firewall.
Right.
Okay.
Well,
Okay. So is that a problem or not? And honestly, I pretty much trust the government of that country to not shut it down. But the whole point of Bitcoin was to not have to trust anybody. So the fact that we have to now trust a single party is kind of annoying. Yeah. So it's, okay. Yes?
So do you have any pilot running? And if so, what is the volume, how many transactions, how many tokens from Hashgraph have you transacted already?
We do not have a public network. We have the private network. Anybody can download it. You can download it right now, and you'll see on your computer you're getting hundreds of thousands of transactions a second. That's just your computer talking to itself. So you can pretend that your computer is 4 computers all running on one machine, and you'll see 250,000 transactions per second if you run our software. Or you can get AWS instances, and you can run them all in one region, or in 2 regions on opposite sides of the United States, or in 8 regions spread around the country, around the globe. From Tokyo to Canada to South America to Berlin and South Korea and East Coast and West Coast. If that's 8, those are the 8 we did. And what we found was good speed numbers. And there's lots of trade-offs, and we can talk about what the exact speed numbers are. I've kind of alluded to them. We are at this very moment, I have one of our guys running a big, complicated set of experiments on AWS so that we can publish this. And we're going to publish it with all the caveats. And I want to emphasize again what I said before. It's the consensus part of this that is so amazingly fast that it's not going to be your barrier. So what really is going to be your barrier is how fast the computers themselves are, probably, your bandwidth and your processing speed. But the network itself isn't really going to cost you very much for consensus. But yes, we've tested that. Yes?
Yeah, this is more a higher level question. So, you know, like blockchain already became like a buzzword for banking industry, like every bank's using blockchain. I was curious from your perspective, what does it mean? What is the current progress that the banking adopted blockchain? And then where do you see as the most potential for banking maybe in the future for this technology application?
Yeah, for whatever reason, we have the majority of our customers are in the banking and financial services and payments industry. I'm not entirely sure why they're first, maybe because Bitcoin was a cryptocurrency, so they just sort of started. But for whatever reason, the fintech and Fiserv industry is the leader in this. One of the leaders, but there's others coming alongside that are interesting. Actually, some really interesting stuff going on. If you're part of this blockchain club, then I'm sure you're aware that there's really cool things going on. What we have been finding is that there's enormous interest. So basically, everybody in that industry has a team, every big company has a team looking at blockchain. What we also keep hearing is they're saying, we're not ready yet, or blockchain isn't ready yet. It's not we're not ready, it's they're not ready for us. That they want blockchain to have greater speed and lower transaction costs and some of these other things first. And then we start talking about security and they say, oh yeah, add that to the list. So that's what we're finding. So you're asking what are the...
Maybe what are the current applications in banking?
Yeah.
And what are the future applications that have the most potential?
Yes. The future is easy. I think that it's basically going to change everything. You won't use, not everything will end up without a server and without a network, but lots of things in every industry are going to go from a central server to a distributed because there's sort of no cost to doing so in most cases and huge benefits. So where will they end up using it in the long run? For everything, I think. In the short run, the funny thing is that industry is also really into NDAs, especially about their use cases. I can say they are very interested in transferring money or value. They are very interested in records, as in audit records and things. They are very interested in any kind of shared data that other parties are interested in. So, you know, there's cooperation between people in an industry, different companies in an industry, and you trust each other, but not a whole lot. And so maybe you and I trust each other to share some information, but I don't want to trust you to never corrupt my database. And so this is the kinds of things that I'm seeing. Yeah, and those are really vague answers, and I'm sorry. The short answer would be, you know, all the media hype about all the things you might use blockchain for? Yeah, people are interested in those things, and they're going to happen eventually. And like all hype, it'll be slower than the hype suggests, but then it'll happen fast.
Thank you.
Are you planning to do an ICO or to, you know, get the Hashgraph token out in the market?
Yeah, so right now, we have a consensus algorithm, we have a platform we built on it, and we're doing permissioned ledgers, and we are thinking about other things, and we'll be talking in the future about other things.
Okay.
And as you might have guessed, that wasn't the first time I've heard that question.
Okay. So yeah, just understand, so what is your go-to-market strategy? Because you seem to be more towards the enterprise.
Well, right now our go-to-market strategy is the permission network side, and we have more people interested than we can even handle. We are finding that the pent-up demand for a fast and secure private network is overwhelming for permissioned ledgers. But we're also interested in other things as well.
So building up on that point,
yes.
At the end of the day, what would be your product? Would it be the consulting services that you provide to enterprises?
No,
would it be a standalone cloud infrastructure?
Okay, there are many directions to go in the future, including public networks. Right now, we have a platform. It is a program that the customer puts it on all their computers and their competitors' computers, whoever's talking to each other, and then they can write an app that does the business logic of interpreting what the transactions actually mean to them, And our platform is the consensus engine that then allows the app to create a transaction, and then the app can rest assured that it will get spread to everybody, everybody will come to an agreement, and then when we all know the order and the timestamp, the app will be told, here's the official order and here's the timestamp, and the app can do something. What we have found is that the platform we've built actually makes it really easy to write apps. We have 6 example apps with source code. We have customers. One of our early customers, actually, one of our early customers said, okay, we'll download from your website, your platform. Then they went away and we didn't hear from them for a couple of weeks, and they came back and they said, yep, we wrote our app and it was just as easy to write as you said. Didn't have to have any help, didn't have any hand-holding. They just went off and wrote it and it worked and they liked it. So right now, what we are doing is licensing this platform and then people build apps on top of it. You could imagine a host of different business models that could be pursued in the future. And we are just taking what we believe the logical approach to them. And right now, we're doing what I just said. Does that answer your question? No. Kinda. Okay.
So what I'm interested to hear about is basically, I know I worked in VC before and I worked with open source companies.
Yes.
So they have a separate model how they distribute and how they make money.
Yes.
So my question, like at the end of the day, would be how would you make money? Would you sell licenses or?
Yes. We sell licenses to the platform.
Got it.
People pay us.
That answers.
Yes. Yes. I understand. Sorry. Right. We are licensing the platform for people to build apps on top of. Yes. And you mentioned VC. Our seed round was $3 million, led by NEA. And so, they're a big VC firm.
Yeah, that's why I asked, basically. I know that they would not back up something that has no business model embedded at this particular stage.
You are correct, right. And you never want to have, I have about 1 million ideas for business models. As a startup, that's a very bad idea. What you want to do is start by saying, I'm going to build a search engine, and then eventually you become Alphabet. But you don't start as Alphabet. I guarantee you that our goal is to start with a search engine, but to end up being Alphabet. That's our goal. Yes?
The current format of your platform, does that allow for smart contracts and like executionable kind of transactions? Or is that something for the app builder to build on top?
Yeah. So the app, in a sense, is like a smart contract. This is sort of a different way of doing smart contracts. But you could also talk about building an app that is an EVM for smart contracts and then separated into 2 layers. So then you have smart contract scripts that run on top of the app that is the interpreter for the scripts. So all of that is a layer above what we are at right now. So at the moment, we're not selling that, and we haven't published algorithms for that yet. But obviously, the core thing you need for that is the ability to put transactions in order. So, a consensus algorithm is one piece of what you need for smart contracts. And smart contracts are important for any big system.
So when Hashgraph becomes the alphabet that you'd like it to be, is there still Bitcoin and Ethereum, or does it kind of swallow up all these other?
I don't know. There's always room for more than one player, right? So when Ethereum came along, it didn't kill Bitcoin. Bitcoin's doing pretty well. So, there may be room for multiple people. I don't know. Typically, the history of any kind of market is that you have this enormous springing up of thousands and thousands of companies, and then you have a crash, and then you get down to 3 or 4, whatever, big companies that continue on there. And that's the way every revolution tends to happen. I'm sure we'll see the same pattern here. Yes?
So do you think you will compete with Bitcoin and Ethereum?
Okay, so Bitcoin is not a permission ledger. We're doing a permission ledger. And our permission ledger is doing really well when we compete against other permission ledgers. In the future, maybe we would do a public ledger and then ask me then, and I'll tell you how we did. But right now we're doing permission ledgers. And we are finding that we are very competitive as a permission ledger for reasons you might guess from the talk.
Yeah. And what about so people use Ethereum as a platform because of the solidity and the computer, worldwide computer, because that's the vision of Italy inputting. Do you think it makes sense to Hashgraph to go into this direction as well, or just stay in this more, narrow distributed asset?
Yes, you just asked me, should we someday have a public ledger?
No,
that's not a bad idea.
Ledger. So Ethereum is known for being a platform in which you can use the Solidity language to build the smart contracts. Question is, do you think this will fit the technology of Hashgraph as well?
Yes, you could build all the parts of a public ledger on top of us. So What you're talking about is smart contracts. You could have a public ledger with smart contracts. You could have a public ledger with a cryptocurrency. You could have a public ledger with a sharded file system and with other forms of sharding and a distributed hash table. All of those pieces you could do public. You could also do permissioned versions of all those pieces, including a permissioned Ethereum Solidity interpreter. But you know what? What we have right now is actually doing the first step of that anyway. We have a platform that makes it really easy to build these apps. You could view these apps as being like smart contracts themselves. But there's not smart contracts that are coming in from outside users. So it's sort of a permissioned version of smart contracts. So right now what we're having is doing the permissioned version of that, but not the public version of that. In the future, we might expand out to further things. But at the moment, what we're finding is we are trying to do what a startup does, which is you go with what your customers are really asking for right now. So what we are doing is what our customers are really asking for right now. And they say, we love the ability to build these little apps in Java, and you made it very easy for us. They're not asking, please let me build these little apps in Solidity and have them interpreted. If they were asking very loudly, we would prioritize when we did that sort of thing. But right now, it hasn't been what they're asking for. In the long run, we would do everything, right? But right now, we're just doing the thing that the customers are actually asking for. Well, I appreciate your patience, and I appreciate all the time. You guys gave us an hour and a half. I appreciate you coming and showing interest, and feel free to look at our website. We've got math stuff, we've got videos, and we have someday this video maybe. And if they let us have it, I think they're going to let us have it. We'll put it on our website. If not, it's probably on a Harvard website. But I appreciate this, and thank you very much for letting me come here.